All right, our lesson now is on multiplying and dividing radicals. We're going to start with multiplying. Multiply. Square root 2 times square root 3 minus 5. Okay, in this example, we're just going to actually distribute. The square root of 2 times the square root of 3 is the square root of 6 minus the square root of 2 times 5. Now notice the 5 is not under a radical, so the 5 is on the outside. It's 5 times square root 2, like that. Now since I can't simplify the square root of 6, these are not like terms, they are unlike terms. I cannot add to them or subtract them, and so that's my answer. I can't do anything else with that. 3 square root 5 squared. Now when you square something, that means that you multiply it to itself, and so this is 3 square root 5 times 3 square root 5. I can rearrange these terms, though you could leave this step out. That's 3 times 3 times square root 5 times square root 5. 9. And the square root of 5 times the square root of 5 is the square root of 25, but that's just 5. So 9 times 5, our answer here is 45. 45. Here's another. The square root of 6 times the square root of 10. Well, if I use my multiplication rule for radicals, that's the square root of 60. But sometimes you can simplify a radical after you multiply two of them together. And so if I simplify this, I get, let's see, a perfect square in 60 would be 4. I think 4 is the largest perfect square. It's 4 times 15. The square root of 4 is 2. And so this is 2 square root 15. So after you multiply, always remember to simplify the radical if possible. Square root 5 plus 3 times square root 6 plus 1. To multiply this together, I can use the FOIL method. FOIL this out. Square root 5 times square root 6. That's the square root of 30. 5 times 6, 30. Square root 30. Square root 5 times 1. That's just a square root 5. 3 times the square root of 6. 3 square root 6. And then 3 times a 1 is a 3. Now I cannot simplify any of those radicals, and they are all different, and so I cannot combine any of them. That is my answer. It doesn't simplify any farther than that. Cannot simplify further. Let's try another one like that. Square root 10 plus 3 times 5 minus square root 10. Okay, once again, I'm going to use the FOIL method. Let's see what we get here. The square root of 10 times a 5 is 5 square root 10. Square root 10, or minus, there's a minus sign there, negative. Square root 10 times square root 10 is the square root of 100. 3 times 5 is 15. I'll change the color here. 15. And then finally, 3 times negative square root 10 is going to give us minus 3 square root 10. Now we can combine a few things here. First of all, I notice that 5 5 square root 10 minus 3 square root 10 is 2 square root 10. I also notice here that that's actually minus 10. Right? Square root of 100 is 10. Plus 15, I can add those numbers together, and I'll get my answer. That's there and that's there. I'll get my answer 2 square root 10 plus 5. And there's our result. Here's another. Square root 7 plus square root 3. Square root 7 minus square root 3. Once again, it's the FOIL method that I'm going to use. The square root of 7 times the square root of 7 is the square root of 49. That's going to be square root of 7 times negative square root of 3. That's minus square root of 21. Square root of 3 times square root of 7 is positive square root of 21. And then finally, we've got square root of 3 times negative square root of 3. That's negative square root of 9. Like that. Now let's simplify. Square root of 49 is 7. Notice that I have a negative square root of 21 and a positive, and so those cancel away. That's 0. Minus the square root of 9 is a 3. 7 minus 3 is 4. And so that one just multiplies out to 4. Square root 5 minus 2, quantity squared. Now remember, when we square something, we multiply it to itself. So this is square root 5 minus 2 times square root 5 minus 2. FOIL method again. The square root of 5 times the square root of 5 is the square root of 25 minus 2 square root 5. This times this is another minus 2 square root 5. And then negative 2 times negative 2 is a positive 4. Okay, so I have it all FOILed out. The square root of 25 here is a 5. I can combine these two terms together. That's going to be negative 4 square root 5s. And then plus 4 on the end. I can add the 5 and the 4 together to get 9. And so I'll have my result 9 minus 4 square root 5. And there it is. Okay. Let's try one with a cube root in it. Four plus cube root 2 times 4 minus cube root 2. FOIL method. 4 times 4 is 16. 4 times a negative cube root 2 is a negative 4 cube root 2. Cube root 2 times a 4, positive 4 cube root 2. And then finally, we've got cube root 2 times negative cube root 2 is going to be a negative cube root of 4. Notice that these two terms do cancel themselves out, and I'm left with 16 minus a cube root 4. And there's no perfect cube in 4, so it cannot be simplified any further than that. Okay, very good. Okay, moving on. These were all examples of multiplying radicals. Now we're going to look at some dividing. And a special case of that is where we rationalize. It's called rationalize the denominator. They look like division problems, but really what most texts would say is rationalize the denominator. And what we mean by that is we cannot have any radicals in the denominator when we're done. No radicals in the denominator. If there is a radical in the denominator, it's not considered simplified. Example of that, let's say we have 3 over square root 2, or 3 divided by square root 2. I need to get the radical out of the denominator, so what I'm going to do is multiply this by something equal to 1. And what I'm going to do is I'm going to multiply this by square root 2 over square root 2. Because if I do that, if I multiply square root 2 to a square root 2 down here, that will give me the square root of 4, and I've created a perfect square. Which is going to be 2 in a minute. In the numerator, we got 3 times square root 2, which is just 3 square root 2. But the denominator is a 2, so we got 3 square root 2 over 2. And it is rationalized because there's no longer a radical in the denominator. Here's another one similar to that. 2 over square root 7. To rationalize the denominator here, I'm going to multiply by square root 7 over square root 7. Remember, you have to multiply by something equivalent to 1 here for these fractions. In the numerator, I've got 2 square root 7. In the denominator, I've created a perfect square. It's the square root of 49. And so this is going to be 2 square root 7 over 7, and we have it rationalized again. Square root 5 over square root 3. Okay, to get rid of the radical, I'm going to multiply by square root 3 over square root 3, like that. In the numerator, I'm going to have the square root of 5 times 3, which is 15. In the denominator, I've got the square root of 9. The square root of 15 cannot be simplified. However, the square root of 9 is 3, and I've rationalized it. All right, moving on, a couple more. If I have the square root of, let's say, 1/8. Now, if I use the quotient rule, the square root of 1/8 is the same as the square root of 1 over the square root of 8. Square root of 1 is 1, by the way. Now, there's two options here. I could multiply both top and bottom by square root 8 right now, or I could multiply by square root 2 over square root 2. I'll show you both methods. Either one's going to get us the right result. Most people would probably multiply by square root 8 over square root 8, which is fine. In the numerator, I have the square root of 8. In the denominator, I have the square root of 64. And so I got square root 8 over an 8. But we're not done, and that is because the square root of 8 here can be simplified. Since 8 is 4 times 2, the square root of 4 is 2. That simplifies, the numerator simplifies to 2 square root 2 over 8. And then I can reduce right here, since it's all multiplication here, I can reduce that 2 over 8 is a 4, and so my result is going to be the square root of 2 over 4, like that. Another method is to do it this way. I use the quotient rule again and write it as square root 1 over square root 8. But remember, my goal is to create a perfect square down here. I want a perfect square there, and so if I multiply 8 by just 2, I can make a 16. That's a perfect square. So I'm going to multiply this by square root 2 over square root 2. Because 8 times 2 is going to be a perfect square. If I do this, in the numerator we have the square root of 2. In the denominator we have the square root of 16. And the square root of 16 is 4, and so we got square root 2 over 4. Notice how this method was a bit faster, but you had to figure out here that I had to multiply the 8 to a 2 to create a perfect square. Let's fit another one in over here. 3 over square root 48. Now what I might try to do on this one is simplify the radical first before I attempt to rationalize. Right, remember on all these we're rationalizing the denominator. Square root of 48. A perfect square in 48 is 16. 16 times 3 actually. And so the square root of 16 is 4. So we've got 3 over 4 square root 3. Okay, so I've worked it down to that. Now, to eliminate the radical in the denominator, all you really have to multiply it by is square root 3 over square root 3. If I do that, I get 3 square root 3 in the numerator. In the denominator, I've got a 4, and then a square root 3 times a square root 3 is a square root 9. I'm running out of room here. Let's go over here. So that's 3 square root 3 over 4 times 3. Right? Square root of 9 is 3. I can then cancel those 3's, and I am left with the square root of 3 over 4 as my answer. Another approach would have been to multiply the original problem by square root 48 over square root 48, but then you'd have to deal with some larger numbers, and you'd still have to reduce the radical anyway. So either method still will work and get you the correct simplified radical. Let's try one now with a variable. Okay, rationalize or simplify here. Simplify. Square root of 72 over y. Okay, I'm first going to use the quotient rule and write that as the square root of 72 over the square root of y. I need to create a perfect square in the denominator, so what I need is to multiply by square root y over square root y. That'll give me the square root of 72y over the square root of y squared. And notice that a y times a y is a y squared. That is a perfect square. That's the goal here. Perfect square. Assuming everything's positive, the denominator is just y. The square root of y squared is just a y. I can simplify the numerator a little bit. 72 is 36 times 2. And the square root of 36 is a 6. And so we should have left here as our answer 6 square root 2y in the numerator, all divided by a y. And there's our answer. Square root 200k to the 6th over y to the 7th. Let's see if we can, well, we can use the quotient rule first. I'm going to write this as two radicals. Square root 200k to the 6th, square root y to the 7th. Now let's simplify as much as we can first before we multiply by something. $200 is 100 times 2. So if I take the square root of 100, that's a 10. So I've got 10 square root 2. I'm going to use my little shortcut division rule here. 2 goes into 6 exactly 3 times, so I'll have a k cubed on the outside. So the numerator is 10k cubed square root 2. In the denominator down here, 2 goes into 7 3 times, but has a remainder of 1, so there's a y to the first left under there. Now that I have all the radicals simplified, the quickest way to rationalize this denominator is to multiply it by a square root y over square root y. Because that right there will create a perfect square. 10k cubed square root 2y right there under the radical over y cubed times square root y squared. But remember that this is just equal to y, and so I have left as my answer, I'll put it up here, 10k cubed square root 2y, and that's all going to be over a y to the fourth, right? We got a y cubed and a y to the fourth. And we have it rationalized. All the examples we've done so far were rationalizing square roots. Let's try a couple cube roots now. Cube root of 27 over 16. Using the quotient rule, I can write this as the cube root of 27 over the cube root of 16. I'll simplify each radical first. We know that the cube root of 27 is exactly 3. And a perfect cube in 16 is 8. 8 times 2. So cube root 16 is 2 cube root 2. Now, because this is a cube root, in order to get rid of the radical in the denominator, I have to create a perfect cube. If I multiply by cube root 2 over cube root 2, it's not going to work. And the reason is because this right here is a cube root of 4, and that's not a perfect cube. 4 is not a perfect cube. What I have to do is I have to multiply by cube root 2 squared over cube root 2 squared. And that is because to create a perfect cube, I need 3 2's down there. That's going to be the cube root of 8 right here. So I got 3 cube root 4 over 2 cube root 8. The cube root of 8 is 2. This is equal to 2. And so I have as my answer 3 cube root 4 over 2 times 2, 3 cube root 4 over 4. And it's rationalized. Let's look at another one like that. The cube root of 15 over 32. Okay, I'm going to split it into two radicals. Cube root 15, cube root 32. The cube root of 15 I cannot simplify. There's no perfect cubes in it. 32 I can. 32 is 16 times, no, 16 doesn't work. Let's back up. I need a perfect cube, not a square. A perfect cube in 32, it's 8 times 4. The cube root of 8 is 2, so 2 cube root 4. Okay, now it's, we've simplified all the radicals, but I still have to rationalize it. Since we have a cube root here, I need to create a perfect cube. And so what do we multiply 4 by to turn it into a perfect cube? We can multiply it by 2. So I'm going to multiply by cube root 2 over cube root 2. In the numerator, that will give us the cube root of 30. In the denominator, I've got 2 cube root 8, which is a perfect cube. It's 2. And so my answer is going to simplify to cube root 30 over 2 times 2, which is 4. Cube root 30 over 4. Good. Okay, one more like this. Cube root of m squared, or m to the 12th over n. Use the quotient rule, write it as 2 radicals. Cube root m to the 12th over cube root n. The cube root of m to the 12th, using my division shortcut, 3 goes into 12 exactly 4 times. It's m to the 4th over cube root n. Now to rationalize the denominator, I have to create a perfect cube. So to turn n here into a perfect cube, I need 2 more n's. I need to multiply by cube root n squared over cube root n squared. That will work because in the denominator that will create for us a cube root n cubed. In the numerator I've got m to the 4th cube root n squared. Our denominator is just equal to n, and so our answer is m to the 4th cube root n squared over, make that a little smaller, n. And we have it rationalized yet again. Okay, so we've rationalized square roots, we've rationalized cube roots. Let's do one example of a 4th root. 4th root of 5z over x. I'll use the quotient rule first, like I've been doing. This is the 4th root of 5z over the 4th root of x. To rationalize the denominator here, I need to create a perfect 4th down here. And to turn x into a perfect 4th, you will need 3 more x's. So you're going to have to multiply by 4th root x cubed over 4th root x cubed. If we do that, in the numerator we will get the 4th root of 5x cubed z. In the denominator we have the 4th root of x to the 4th. But that, of course, is just an x. And so my answer is the 4th root of 5x cubed z all divided by x. And it's simplified. Good. Okay, moving on. Rationalizing with binomials. For example, 3 over 1 plus radical 2. If I multiply top and bottom by radical 2, that's not going to work. The trick to rationalizing a denominator that has a binomial in it, such as 1 plus square root 2, is to multiply by what's called the conjugate. The conjugate of 1 plus square root 2 is 1 minus square root 2. You just change the plus sign to a minus sign or a minus sign to a plus sign. And notice I'm still multiplying by something equivalent to 1. Multiplying by the conjugate will always work in cases like this. Let's work out what we have in the numerator. In the numerator we got 3 times 1 minus square root 2. In the denominator, we have to FOIL that out, but notice that it's one of those difference of squares patterns. So the 2 middle terms always cancel. Difference of squares. And so multiplying it out, I'm going to have 1 times 1, which is 1. The 2 middle terms cancel. I won't even write them down. I just go to the last terms. Minus square root 2 times 2 is 4. Notice that I've got in the denominator square root of 4, which is 2. That's a 2 there. And so I got 1 minus 2, and my answer is 3 times 1 minus square root 2 all over negative 1. Which you could leave like that, or you could write that as negative 3, 1 minus square root 2, right? Dividing by a negative 1 is the same as multiplying by a negative 1. So this or this is our acceptable answer. But notice that we no longer have a radical in the denominator. Here's another one. Five over 4 minus square root 3. To simplify this fraction, I'm going to multiply top and bottom by the conjugate. Four plus square root 3 over 4 plus square root 3. So if I put this together, I get 5 times 4 plus square root 3 in the numerator over. Down here is our difference of squares pattern. So that's going to be 4 times 4 is 16, minus square root 3 times square root 3 is square root 9. 5 times 4 plus square root 3, all over 16 minus 3, which is 13. So my answer is going to be 5 times 4 plus square root 3, all over 13. You could distribute the 5 if you want to, but it is not necessary. That will be good enough. Okay, let's look at a couple more of these. $15 over square root 7 plus square root 2. Once again, I'm going to multiply by the conjugate. So that's going to be square root 7 minus square root 2 over square root 7 minus square root 2. In the numerator, we got 15 times square root 7 minus square root 2. In the denominator, we have our difference of squares pattern. So square root 7 times square root 7 is square root 49. And minus square root 2 times square root 2 is minus square root 4. 15 times square root 7 minus square root 2, all over 7 minus 2, which is a 5. All divided by 5. And this one actually I can reduce here. Notice that I can reduce that. 15 over 5 reduces to 3. And so my answer is 3 square root 7 minus square root 2. There it is. One more example of multiplying by the conjugate. Square root 3 minus square root 2 over square root 3 plus square root 2. Let's see what we get with this. So I'm going to multiply by the conjugate of the denominator, which is going to give me, or which is going to be, square root 3 minus square root 2 over square root 3 minus square root 2. In the denominator, I have my difference of squares pattern right here. So it's we're going to have square root 3 times square root 3, that's square root 9, minus square root 2 times square root 2 is square root 4. In the numerator, I've got to FOIL this out. Square root 3 times square root 3 is square root 9. Square root 3 times negative square root 2 is negative square root 6. This times this is another negative square root 6. And then finally, negative square root 2 times a negative square root 2 is a positive square root 4. That is a 3 plus 4, square root 4 is a 2. I'll put that up in the front here. 2. Those combine to be negative 2 square root 6. In the denominator, I have 3 minus 2. I can add those two numbers together there. By the way, you can't subtract those 2's because one has a radical 6 on it, the other doesn't. So my answer is going to be 5 minus 2 square root 6 over a 1, and so that is my answer. And that is how we multiply and divide radicals into the lesson.